Welcome to today's lecture on solving the two-dimensional heat equation using the finite difference method, both computationally with the MATLAB and manually. The two-dimensional heat equation governs the distribution of temperature over 2D. Reason is the function of time, influenced by thermal conductivity and initial boundary value conditions. We will explore how to discretize this partial differential equation in space and time using finite difference, constructing iterative scheme for numerical solutions. By delving into MATLAB implementation, we will harness its computational power for efficient simulation, while the manual approach will deepen our understanding of the underlying principle and numerical stability. Through this comprehensive study, we aim to equip ourselves with the practical tools to model and analyze complex heat transfer phenomena in various engineering and scientific contexts. Here we are going to discuss about how we can solve two-dimensional heat equation using finite difference method with MATLAB as well as manually. So here we have the two-dimensional heat equation describes how temperature changes over time in two-dimensional domain and is given in equation number 1. Del U upon del T is equal to alpha into del to U upon del x square plus del to U upon del y square, where U, x, y, T is the temperature distribution at position x, y and time T. Alpha is the thermal diffusivity constant. So first we need to discretize the domain, divide the special domain into the grid point x, y, j, and where I will be equal to 1 to m and j will be equal to 1 to n. And also we need to discretize the time domain. Tn will be equal to n dot delta t, where n will be equal to 0, 1, 2, 3 up to n. Delta t is the time step, and the grid spacing we have is delta x and delta y along x-axis and along y-axis. Now we need to apply the initial condition and the boundary conditions. So first we need to set the initial temperature when we have t is equal to 0. U x y 0 is equal to fxy, and fxy is the initial temperature distribution when time is 0. Then after, along with we are given the boundary condition. So here we can observe that this is the first boundary condition, which is the left when x is 0 and y varies from its domain and the time is t. But remember that t is greater than 0 in each case. Okay, so this is the left boundary condition and this is the right boundary condition. Suppose that we have the here is x equal to 0 and here is x equal to L. So here the left boundary and right boundary values are given. So and this is the lower boundary on the when we have y is equal to 0. Okay, and this is the upper boundary when y is equal to h. When y is 0, we have u x 0t is equal to g3 xt, and when we have y is equal to h, then we have g4 xt. So according to that, for the first two cases, we can see that g1 and g2 both are the functions of yt, and the last two we have g3 and g4 both are functions of xt. Now for the difference approximation, we need central difference for the spatial, which are given in the first expression. You can see here del to u upon del x square will approximate ui plus 1 j minus 2 uij plus ui minus 1 j upon del x square, and this is the with respect to y, del to u upon del y square is approximate to ui j plus 1 minus 2 uij plus uij minus 1 upon del y square. For the time derivative, we have the forward difference, and which is given as del u upon del t is approximate to un plus 1 ij minus un ij upon delta t. Okay, so by putting these three expressions in the given heat equation will reduce in this form, and this is the most important equation. All the values will be approximated by using this equation. Here we have chosen one example to solve the two-dimensional heat equation with the given initial condition and the boundary conditions using the finite difference. So here are the initial conditions. When t is 0, u x y 0 is equal to sine 2 pi x, sine 2 pi for the domain 0 less than x comma y less than 1, and the boundary conditions when t is greater than 0 for all the boundaries u x y t is equal to 0, and we are considering here the thermal diffusivity constant is alpha equal to 1. Okay, now now from these conditions we will discretize. So divide the domain into the grid spacing delta x delta y is equal to h, and n are the intervals used in both x and y. So the resulting the grid we have n plus 1 by n plus 1 points. So these points will be there when we will discretize the domain, and the grid point will be this order. And finite difference approximation we are using here, and will be u n plus 1 ij minus u n ij upon delta t will be equal to this one. So alpha u n I plus 1 j minus 2 u n I j plus u n I minus 1 j upon h square plus u n I j plus 1 minus 2 u n I j plus u n I j minus 1 upon square. We need to update this equation for this expression u n plus 1 ij, which will be on the next slide. So here you can see that the updated equation for u ij n plus 1, so which will be equal to this equation number 2. This is the equation number 2. Okay, only this equation is required to get all the approximated value which is based on the finite difference scheme, and after that we need iterative solution, implement the update equation in the numerical solver to compute the temperature distribution over time. To implement finite difference method, first we need to discuss here this diagram, how we will implement this method. So here when t is 0, when time is 0, index for time we are using 1. This is the index 1 in each case. Okay, you can see on the boundary points as well as the interior points. Now here on the x-axis we divide in 5-point grid initially. Okay, and here is x equal to 0, then this is 0.25, this is 0.5, 0.75, and this is 1. But we are giving here the index for x corresponding to this point we have is 1. This is the index for x. This is an index for next value 2, 3, 4, and 5. So these are the index for this point. And similarly on x-axis we have y is equal to 0, and the index for this value we have is 1. So this is the index for y, you can see. So these are the boundary values on x-axis, and this is the boundary values. You can see here u115. Okay, this is u125, this is u135, u145, and u155. Okay, so and also on this y direction you can see here this is u11, and here is the index for y is 2. This is the third point, this is the fourth point, and similarly on this side these are the values at which we need to compute. If we are choosing u111, what is the meaning of this expression? The meaning is that this is the index for 1. It means x1 is equal to 0. This is the current point. Okay, and y1 is equal to 0, 0, and 0, and this is the time index which is also 0. Okay, if you have the point u121, the meaning is that x2 is equal to 0.25, and y1 is equal to 0, and the time is also 0. So this will be u 0.25, 0, and 0. So in this way we symbolize every grid point. Okay, and we are given all the boundary values, and in the blue plane these are the initial conditions. At this place we need to apply the initial condition, and by applying the initial condition we can easily compute all these points which are inside this plane as well as the boundary point. And this is very simple way to compute all this after applying the initial condition. And in the red plane, you can see this is the next level. When we have t is equal to 0.25, this is the next level. Okay, and these values will be corresponding to at this place also. So the grids which you can see in the blue plane, in the red plane, and in the green plane, all these are identical. Okay, but only the function value will change when we will use. This is only for the just understanding how we are implementing for the next level to get the values. Okay, so if you need to compute these values, we will use our method which we established just now. And all these values are required to compute all these points in the red plane at the grid points. Okay, and also we are given that when t is greater than 0, boundary values, these are the boundary values, and each boundary value at this place you can see will be 0. Only we need to compute the values at the interior points. You can see these are the interior point, only the values at interior point we need to compute. So this is all about this diagram, and we will follow everything which we discuss here in this diagram. Okay, now here is the main implementation, how we can implement manually, and see here very carefully. Every step has been explained one by one. So first we have the grid values of u, x, y, t for t is equal to 0. We denote the symbol u1 ij. Okay, 1 is used for when t is 0 is equal to u, x, I, yj is equal to 0, where ij will vary from 1, 2, 3, 4, 5. Okay, then we have to apply the initial condition, and you can see that u, x, y0 is equal to sine 2 pi x sine 2 pi y, and xy lies between 0 and 1. Step size we have is h equal to 0.25. So by following this one, x1 y1 will be equal to 0, x2 y2 will be equal to 0.25, x3 y3 will be equal to 0.5, x4 y4 will be equal to 0.75, and x5 y5 will be equal to 1. These are the indexed and their corresponding values. See here, we needed to compute the grid point for y1 is equal to 0 and t is equal to 0. So as we symbolize every grid point in the diagram, and corresponding to that when t is 0 and y1 is equal to 0, you can see in each expression y1 is fixed. Okay, x1 y1, x2 y2, x3 y3, x4 y4, x5 y5. So all these points are on the x-axis where y is 0. Okay, and all these values are we have is 0. Also at the place when we have y5 is equal to 1 and t is equal to 0. So this is the upper value. Okay, and in each case we have y5 is fixed, and x1, x2, x3, x4, x5, these are varying, and all these values are also will be equal to 0. And very simply we can check it by using the equation. You will have this value 0. Values at the grid point for x1 is equal to 0 and t is equal to 0. These values are also will be equal to 0, since in the equation one variable when we have 0 is 0, and if it is equal to 1, then also the values will be 0. So you can see here when we have x0, then all the values are also 0, corresponding to all these points which we have shown in the diagram. Also when we have x5 is equal to 1 and t is equal to 0, all these values are also 0. You can see in the equation number 18 to 22. Now when we have y2 is equal to 0.25 and t is equal to 0, the corresponding to this one, the expression which is for t equal to 0, we have the index is 1, and x, the meaning of this one is we have 0 and 0.25. Okay, so the value of x1 is 0 and that of y2 we have is 0.25, and put these values in the given initial equation. Okay, so when you will simplify, this will be equal to 0. Similarly for this value u1 22, and when you will put these values, and the value of x2 we have is 0.25, this is also 0.25, and when you will simplify, this will be equal to 1. Similarly, we can get the values of the other expression, which are very quite simple. You can take the help of MATLAB as well as the calculator. Okay, so all these values has been computed here corresponding to this expression. Y2 is equal to 0.25 and t is equal to 0. Here also we are computing when y3 is equal to y is equal to 0.5 and t is equal to 0. In the same way, we are computing the value of u113. Here is x3, y3 and 0. Okay, put these values in the given equation, and you know sine 0 is 0, so it will be automatically equal to 0. Similarly, you can compute the value of u123, u133, u14 and u53. Okay, so this value and this value will be are the boundary values, so that's why these always will be 0 and these are non-zero values. And also value at the grid point when we have y4 is equal to 0.75 and t is equal to 0, and we have the expression u114, which will be ux1 y4, and at this point we need to compute the value of u, and you can see that this will be equal to 0 since this value is 0. Similarly, you can compute these values, which are very simple to compute. Okay, now after computing all these values, what we have to do, this is very important. Now when all the values at the grid point has been computed for t equal to 0, now it is time to compute the value of u x y t for t is greater than 0. So here we are taking the next level. Okay, and for the next level we are taking here t is equal to 0.25, and also you need to remember that when t is greater than 0, we have the boundary values will be equal to 0. u x y t is equal to 0. Once again, you can come back to the diagram. See in this diagram, so this is the t is equal to 0.25, and the values at this boundary point, which I am doing highlight, circles are assigned here. The value will be, these are the boundary point, and each these boundary point the values are 0. Just we need to compute the values at the interior point. This one, at this point we need to compute the values. Okay, so now for that when we have the t is greater than 0, we are choosing here h is equal to delta t, which is 0.25, alpha is equal to 1, and the index for this level we have is n equal to 1. We have to choose to get to the next level. Okay, so the equation will be reduced to in this form. You can say when we have is n equal to 1, the equation 2 will be reduced to in this form. The equation number 38, you can see u2ij will be equal to u1ij alpha delta t upon h square u1i plus 1j plus u1i minus 1j plus u1ij plus 1 plus u1ij minus 1 minus 4u1 I plus 1. Okay, so these values we have already compute in the previous equations. Okay, all these values already has been computed, and with the help of these values we can easily compute the value for next level. Okay, so for that what we need to compute only the values at the interior grid points, and suppose we want to get the value for this expression u22. What I will do, where I have to choose I equal to 2, j equal to 2, the above this equation will reduce in this form. You can see equation number 39, and the right hand side we have is 122 u132 u12 u123 u121 minus 4 u1 2. And all these values we have already computed in the above equations. We have the value of alpha is equal to 1. We have the value of delta, which is delta t is equal to 0.25, and the value of h we have is also 0.25. Now when you will put all these values in the right hand side, and after simplifying, you will get the value of u22, which is 0.36, and so on. Similarly, by using the same process, you can easily get the values on each grid point for u, x, y, t. Okay, but due to the lack of time, I am not doing all the values. Now follow the step which I have just explained in the equation number 39. By using the same, you can get the value at each every point. Now we are going to implement this process in the MATLAB. So here we are going to discuss about the MATLAB implementation. You do 0 less than x comma y less than 1. So the length of each domain we have is equal to 1, and number of the grid point in each direction we are choosing here, n is equal to 5, and the grid spacing we have is dx is equal to L upon n minus 1. So dx will be equal to 0.25 by using this formula, and dy will also be equal to 0.25. Alpha is equal to, we have is the 1, which is the thermal diffusivity constant. dt also we are choosing here 0.25, and t is equal to 1 is the final time. Now to apply the initial condition, we need to generate the mesh grid. This will get, we will get the all these points by using the mesh grid according to our division. So when we will by using this mesh grid, we have all these points, and at this point we need to compute the initial temperature by using the given initial condition. Okay, so after applying this mesh grid value, we can easily get the values of u at the initial by applying the initial condition. Now here you can see these are the boundary conditions, and when we have t is greater than 0, in that case all the values will remain 0. So these are the boundary conditions. You can see u colon 1 is equal to 0, u, and this will be the when y equal to 0, we have this expression. When y, we have y is equal to L, this is the end point. Okay, and then we have x equal to 0, we have u1 colon is equal to 0, and u and colon is equal to 0. These are the boundary conditions. So by these equations, we can easily get the every boundary values when t is greater than 0. The updated equation which we discussed in the previous slide, this is the main equation you can see, which is obtained from the updated equation. Okay, this is the left hand side. This is the new value, new ij. Okay, and this is the right hand side, uij alpha dt upon dx square. Okay, in the place of h we are using here dx, and this is the ui plus 1j, ui minus 1j, uij plus 1, uij minus 1, and minus 4 uij. So here we need to compute only the interior point. See once again here we have, suppose that these are, so here this is 1, 2, 3, 4, and 5. 5 index are there, and 2, 3, 4, and 5. So these are the interior point 2 to 4. Okay, that's why we are using here j will vary from 2 to n minus 1. Okay, similarly I will vary from 2 to n minus 1. So these values will be computed for the interior point, and the updated value, this new value will be stored at this place, which will be equal to u. Okay, new value will be equal to u, and this value again will come back at its place. Since we apply the while condition here, okay, the solution will initialize for t equal to 0 and will go up to the t is equal to 1. Okay, so as soon as we will have t is less than t, and the next value will be computed here, which will be the value for t is equal to 1. Okay, and here the all the new values will be stored at this place after updating every value. U is equal to u new. and t is equal to, we have is t plus delta t. So this is the entire program to implement our finite difference updated equation. Now by using this sequence of statement, we can easily plot the graph for this problem. So these are the sequence of the statement to plot the graph. First, you can see that here is the surface x, y. X and y are the values of x and y, and here is the u function. The value of u are stored at this place. Okay, and x label is there, y label is there, and z label is time. Okay, and then we have the title and box on. So now when we will execute these all sequence of statement, which you can observe from starting to last, we are going to run the program now. Just press at this place, and you can see that we have this graph corresponding to the grid point which we choose here, but we can as possible as we have the small step size, we have more accurate values. Just what we have to do, we need to increase the number of the grid point. Here we are choosing the 10, so this will be more refined that you can observe in this diagram. Okay, and if we have at this place 50, so these are the more number of point, and as much we have more number of point or grid point, we have more accurate values. See once again by running the code. Yes, you can see this is the solution set of our problem. Okay, so now after changing these values, you can do numerous experiment, and also you can rotate this diagram from click from this place, and here you can see this is the entire solution, and now you can play this code. So this is the more accurate solution for this heat equation, as you can see in this diagram. And on the horizontal line you can see one is x-axis and the other is y-axis, and on the vertical line we have the temperature is computed corresponding to the time. Okay, so this is the temperature level you can see. So this is all about the implementation of MATLAB, and implementation is very quite simple. As in conclusion, today's lecture has provided a comprehensive insight into solving the two-dimensional heat equation using the finite difference method, both through computational means using MATLAB and manual method. We have explored the fundamental principles of discretization in space and time, underlying how finite difference approximate derivative, and led to iterative numerical solutions. By leveraging MATLAB's computational capabilities, we can efficiently simulate and analyze heat transfer phenomena in complex systems. Additionally, the manual approach has deepened our understanding of numerical stability consideration and the importance of choosing appropriate discretization scheme. As we conclude, it's crucial to remember that the finite difference method serves as a powerful tool in numerical heat transfer analysis, offering insight into temperature distribution and in the design and automation of thermal system across various engineering and scientific disciplines. Thank you to listen this lecture till the end, and all the content which we present during this session has been uploaded. You can easily download this content from your login account. You can see